Okay, so this is the dreaded circuit problem. I've kind of have a zoomed out view of it. This one is awful. And it was already bad. It was already one of the worst. It's the worst circuit one I've seen because it's got like dialogue. And I made it worse when I recopied it. So if you got any kind of points on it, good for you. I broke it up a little bit in PowerPoint. I just kind of like cropped it in different places to kind of make it a little bit easier to read. So, and to explain. First thing I noticed is that there is a series circuit and there is a parallel circuit, and they call them circuit A and circuit B. Who knows why? So I'm going to put that this one's series. Whoops. And if you remember, series has one loop, and in series, current's constant. Okay, and this one's in parallel. It's parallel. That means it has junctions. And the other thing about this is that series circuits, see how you'd have to, if you were going through here and this is a hallway and somebody had like dropped their bag or was in the way, high-fiving their friends or whatever, but you'd have to go through both of them and it would just, while people are, generally moving at kind of a constant pace around there, it's like a slow, constant pace. Whereas if, imagine this is the hall and oh no, somebody dropped their backpack, but you have like another, like this is the sky bridge, and you have just another one that magically appeared that's just as easy to get to. Even though you have the two people who've dropped stuff or high-fiving their friends and in the way, since people have options of which way to go, everything's going to move a lot faster. So, and the reason why is when you have to go through both in series, you're going to have a much greater resistance. Here, every time, even though you still have the resistor, even if the resistor were bigger, you've added a whole new walkway. So that's like, that would massively improve the flow of anything if you add another path for it to go. So this one has very, I'm going to put minus resistance, very low resistance in parallel. And the more you add in parallel, the lower the resistance goes. Here, the more light bulbs or whatever you put in. It can be light bulbs, speakers, motors, resistors, basically something that just uses up some form of energy or changes it. So let's read the question. Two students compare circuit A to circuit B as shown above. One circuit is connected in series. We already talked about that. The other in parallel. All light bulbs are identical, so I was right on that. Again, sorry I don't get a highlighter, but it just while I'm doing the video, it makes it easier. You can use your blue pen. All light bulbs are identical. That's super useful and are ohmic. That is to say, they follow Ohm's law, yielding a linear curve when potential difference is graphed as a function of current. Hey, guess what? I've seen them put ohmic and they kind of say it follows Ohm's law, but all of this stuff you can scratch out. I just put it there to be mean. And they do that. If you come across something like that and you're like, I don't really think that's important, just ignore it or like scratch it out in pencil. And if you decide it's important, you can erase it later. Ohmic just means follows Ohm's law, which is basically this. We've done this. Just think about current. How does current relate to resistance? The higher the resistance, the slower the current's going to move. How does it relate to potential difference? That's like your voltage in your battery. So 9 volts going to have more current than a 1.5 volt. And you will also see this. It's useful to think of it this way, and this is on the equation sheet, but it's also useful to solve it for potential difference. So you just multiply both sides by R. Um, I'm going to erase that so you can see these. Yeah, if you just multiply both sides times R, you get this. Potential difference equals current times resistance. That's useful to know. Another useful equation to know on this, on any of these things, is power. And just think of power as the VIP room of a club. Now, who all gets in to a VIP room? And it's actually potential difference, delta V I equals capital P, which is power. Well, people who get into the VIP room are usually bright people. Like they all probably have a lot of money because they're powerful. Money's power. Bright people, so they're really smart, like, Silicon Valley people. They can be really hot, like models or actors or actresses. Okay, they can be loud, like singers. And they can also be athletes. So, athletes move around a lot, and they tend to have a lot of fans. You usually see it as a fan, it's just a motor. And if you think about the types of energy associated with this is light, heat, or thermal, sound. This should sound familiar. And then kinetic. So basically, what power does in a circuit is change in energy. So work, it turns electrical energy into one of these forms, and the quicker it does it, the more powerful it is, just like JJ. So this is power. So these two equations are pretty important to remember. This and Ohm's law. So anyway, yeah, so that talks about just that one's in series and one's in parallel. Oh, my dog's mad. Okay, student X states the following. Since a series circuit, oh, I'm sorry, I went the wrong way. Student X and student Y disagree about which circuit will have brighter bulbs. Student X is convinced the series circuit will have brighter bulbs, while student Y is convinced the parallel will be brighter. Okay, that should be interesting. It says student X states the following. Since the series circuit gets all the current from the battery, that's kind of a weird statement right there because usually you say like voltage from the battery, but gets all the current from the battery. Bulbs 1 and 2 get all of the current. That part's true. It's worded funny, but series has a constant current. We wrote that up there. Is constant. That says constant. While bulbs 2, I think that's supposed to say, I cut it off, I'm sorry. Bulbs 3 and 4. Yeah, I totally cut that off. Anyway, basically the other bulbs. While bulbs in the bulbs 3 and 4 will only get half the current. That's actually true. Therefore, the series is brighter. This is the part I disagree with. I don't think the series will be brighter. But I think everything else is true. Okay, student Y counters with the following. But in a parallel circuit, each bulb gets the full voltage from the battery. That is true because of the loop rule. It's like the other bulb is not even there, or doesn't even exist. That's just kind of restating that. Plus, in a series circuit, bulb 1 will use up, this should be a huge red flag, will use up some of the current. Current's not like a use upable thing, it's just like you direct it one way or the other before it reaches bulb 2. So bulbs 3 and 4 will be brighter because they're in parallel. They will be brighter, but I'm pretty sure they'll be brighter, but not for the reasons this person thinks. This used up thing is strange. Okay, so I kind of just had the statement there again. This says, ignore whether the overall prediction is correct. Do not just repeat the student's predictions in your answer. Be real careful about that. Anyway, so this says, which aspects, if any, of student X's prediction are correct? So student X was the one, series gets all of the current. Okay. So series does, that part's correct. And then remember, this is supposed to say 3 and 4. Sorry about that. Cut off. Anyway, it says that 3 and 4 will only get half of the current. Therefore, well, not the series is brighter. I disagree with that. But it's true the other one will only get half of the current. And that's because in parallel, the current, since these are identical, the current's just going to break off into equal amounts. If one of them were bigger, that might not be the case, but since the two bulbs are identical, it's just going to be like split in half. Okay, so I went ahead and answered the questions. It says series circuit will get all of the I current because there's just one loop. Okay, parallel circuit has two equal And I put resistors, then I forgot they were bulbs, then I put bulbs, but it's like bulbs of equal resistance. So I just circled resistors again and put bulbs in parentheses. You can totally do this. This is why we use one line instead of scratch outs. Oh yeah, so anyway, two equal bulbs, which are resistors, one in each branch. Therefore, each will get, I just put I over 2 because I was running out of room. And I put because junction rule and Q equals Q prime because that's what you put when you put the junction rule. All right, I kind of switched some stuff around here. Which aspects, if any, of student Y's prediction are correct? Justify your answer. Okay, so this is the one where student Y said, but in a parallel circuit, each bulb gets the full voltage from the battery. That's true. That's because the loop rule. And there are 2 loops on here. You got like one, or actually 3 technically. You got 1 loop, 2 loops. So like the voltmeter. Okay, so your voltage here will be the same as your voltage here because that's like 1 loop. These 2 have to balance each other out. And then if you look at the great big loop from here to here, I mean, you could look at these 2 as well, but if you look at this great big loop, the battery and this second resistor, it's also going to get the same voltage. That's just how things go in parallel because of the, actually, it's because of the loop rule and E equals E prime. Okay, so that part is correct. Parallel circuit, each bulb gets the full voltage, so yes. Okay, from the battery. It's like the other bulb does not exist. That just seems like extra. I don't know why they put that. Plus, in a series circuit, bulb 1 will use up some. No, 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 no. That is very bad. So I think it's just the, so it says that they're brighter. I think the brighter part's true, but if you remember, it said over here, we're not worried if they're overall. It says, do not, it says, ignore whether they're overall predictions. So the bulbs were their overall predictions. It's kind of vaguely worded. But yeah, so anyway, I think the only aspect that's correct is the voltage thing. Okay. Okay, so all I put is each bulb gets full voltage in parallel because the loop rule equals E prime. If you wanted to draw a picture, elaborate, you can, but that's all you need. Okay, now they want to know which, if any, of student X's prediction is incorrect. Okay, this is weird because they said to ignore the overall prediction that the bulbs will be brighter. But this student was correct about the current in both of them. But right here, therefore, because it says like 3 and 4 will only get half the current, therefore the series must be brighter. It's kind of implied because of the VIP, the power equation. What this person is implying is that because you have delta E I P, they're implying that this current is what's making the bulbs brighter, and that because it splits, that the current in parallel has to be less. What they're basically thinking is that both of these things have the same current, and that's not true because whenever you have something wired in parallel, it has less resistance. Okay, so I'm going to put something about objects in parallel having less overall resistance. It's like they opened up a new sky bridge. And that just because the current gets split, that doesn't mean it's the same in both series and parallel, even if they have identical components. They're wired differently. Okay, this is a tricky one on the wording. I put X, like student X implies that the current total, I total, is equal in both circuits. But the parallel circuit has less resistance and current is inversely proportional to resistance. Therefore, this is false. Okay, so they want to know what part of Y's predictions correct, incorrect, and justify why. And this one is where this person said that bulb 1 uses up current. That's impossible. Current's constant in series, and it's not something that can be used up. The main thing is it's constant in a series circuit, so it's not going to change anywhere. The current's not changing if they're wired that way. So this is what I would put. Okay, so I put in a single loop series circuit, current is constant. Therefore, bulb 1 cannot use up current. So the scoring on these, Okay, Miss Coley was calling to check in, so I guess that's good. Said hi to all first and second, all the other students she knows. So anyway, basically on this, it's a 12-point question, 12-point problem. You can see there's like a ton of letters on it. So they're not worth as much. This first one's worth 2 points. You get 1 point for saying that the series circuit will get all the current and explaining why, because there's just one loop. And then another point for the parallel will get half. On part 2, you get 1 point. Each bulb gets the full voltage, if that's correct, because the loop rule. Let's see. You get 1 point for this, saying that that implied thing about the total current, and then this other one, but you gotta state that. And this one, that the bulb can't use up the current because it's a loop, and that's impossible because current is constant. So, what's that? 1, 2, 3, 4, 5 points at this part. Okay, so it says the student, I guess students, use the equations below to describe each circuit. So the series, they said I total equals I1 equals I2. That's true. Current's constant. I mean, these should be true. And this says that the voltage, and we're assuming that's across the battery, minus, this says I1 R1. Now, if you will recall, the Ohm's law equation is delta V, your change in potential, also called your voltage, equals current times resistance. So basically what this is saying is delta V1 minus delta V2. So they would all equal to 0. And if you solved for these, it's basically saying that the voltage across the battery is the same as the other two voltages. Like if I moved them on the other side, that it balances out. This is your loop rule. Okay. And this is also your loop rule. It's just saying that the voltage is the same in each part. So loop rule. And by the way, it is loop rule, not loophole. I think my other video, it kind of looked like it said loophole, but it's loop rule. And then on this one, it says that current total equals current 3 plus current 4. So that's your junction rule. So that might help out. So anyway, sorry, that's kind of the way it lists all of the equations from above that support students' X prediction. Justify your answer. Okay, and basically my answer for this goes back to here where it said the series circuit will get all of the current and the parallel will split in half, basically. So I said that equations, basically those two things deal with current. So I said that the two current equations Roman numeral 1 and Roman numeral 3, which by the way, I changed those from I think they were 1, 2, 3 in the original or something. I changed them to make it confusing with current. So again, making it harder. Anyway, so those are the two that I picked, and I put current as constant in the single, I should say loop of the series circuit, and then 3. See how I circled these and just wrote kind of brief things? That's all you need to do. I put 3 current splits in parallel circuit because of the junction rule, Q equals Q prime. Okay, so this one says list all the equations from above that support student-wise prediction. And what they mean by that is the aspects of the student-wise reasoning that were correct. So each bulb gets the full voltage because of the loop rule. So if I come down here, I've already written loop and junction rules. So these two are the loop rules, equation 2 and 4. In this particular statement, they are talking about the parallel wiring. So this is the parallel one. I'd probably just put equation 4. Equation 2, I think you can put, but I mean, they weren't even discussing it, so probably not. Okay, so I put equation 4 because it indicates that the potential difference is the same across each bulb, because that's supposed to be a because. Loop rule equals E prime. Here's how this is scored. All right, equation 1 with a reason, plus 1. equation 2, or 3, I'm sorry, with a reason. It needs to be a reason that deals with junction rule, that deals with a single loop in the circuit. 1 point. Equation 4 indicates that the voltage is the same or whatever, that this is the loop rule. You could have 2, I think it said it didn't take off points, but really this is all you need. Best not to write more than what you need. So 3 points there, so we are up to 8 points. So the last one has to be 4 points. Okay, settle the student's arguments by determining which circuit will contain the brighter bulbs. Be sure to use the equations from part B and any other appropriate equations to back up your conclusion. This is sort of like a paragraph answer. Like I said, it's probably 4 points, or it is 4 points, so I'll write it out and explain. All right, it's a little messy, but I think it answers it. Ultimately, student Y is correct. The bulbs in parallel are brighter. The parallel circuit has a greater potential difference because of the loop rule equals E prime. And I realized later I hadn't written an equation, so I found the one that dealt with the loop rule up here, which is 4. And I'm not about to write that all out again because it's free response. I don't have a lot of time. So I just wrote equation 4, just drew an arrow. It also has a greater current because of its lower resistance. And I put that current's inversely proportional to 1 over resistance. And I put that was because of Ohm's law. One more time, Ohm's law is either, you can write it 2 ways. You can write it I equals delta V over R. That's how it is in the equation sheet. Therefore, delta V, your potential difference equals current or times resistance. That's what Ohm's law is. You don't have to write the equation. I just thought it was quicker to write Ohm's law. Then I put the VIP room, your power equation. Change in potential difference times current equals power. So greater potential difference and current mean more power dissipated. Dissipated means like you used up across each bulb. Therefore, brighter bulbs. See how I just like summarized it again at the end just to make sure. So the way that this would be scored in highlighter is like this. Okay, so you get a point for mentioning power somewhere. That's a point. You get a point for relating it back to an equation, mainly equation 4, but you could have used a couple of the other ones kind of just to help support it, but 4 was the big one. You get a point for tying it all together, like down here. And you get a point for picking either potential difference or current to compare it to. I did both, so that's fine. And so that's your 4 points.